Okay, thank you very much for the invitation. It's a pleasure to give this talk on our work on SQIsign. As you may have heard, a lot of people are thinking about and working on quantum safe post-quantum signatures. And SQIsign has recently been remarked as one of the more promising post-quantum schemes for signatures, essentially because of the short key sizes, key and signature sizes. So yeah, what I want to do today is just give a very simple overview. I hope to try, like, nothing is simple in SQIsign, but I will hope to convince you that it is not so, there's not so much. It requires some studying and some entry into it, but it's not as scary as it may sound in the beginning. And so, yeah, let me start from the beginning, which is, of course, elliptic curves. So if you are into cryptography, and before I continue, let me ask, like, the audience here is mostly people who know about cryptography, or is there also other kind of mathematicians?
Yeah, there are other mathematicians, but mostly cryptography. Okay,
so yeah, at any time, do not hesitate to stop me to ask questions. I'm happy to take them. I don't have too many slides, so I guess we can use the time also to keep everyone on board. So yeah, as I was saying, it starts from elliptic curves, and if you are a number theorist or if you're a cryptography, you're very familiar with them. Like here you have the usual picture. You start with elliptic curves, so the Weierstrass cubic, y squared equals x cubed plus ax plus b. A and b are coefficients which parameterize your elliptic curve. You can choose them freely in some fields, and in this drawing here, I chosen them to be in the real numbers. And so what you see on the right is the drawing of an elliptic curve over the real numbers with parameters a and b, which I don't remember how I took them. Some small coefficients, I guess. Why these elliptic curves are so important? They have been a topic of study for 200-300 years at this point. They are related to many topics in analytic number theory, algebraic number theory. They pop up everywhere. And the reason they pop up is that, in a sense, they are the most simple object with a certain kind of structure beyond let's say the finite fields. So, like, you start with finite fields. These are objects which most cryptographers, applied mathematicians are familiar with. You play around with their field structure. They are multiplicative group structure. And then if you want to generalize this to something more general, you have to move to abelian varieties, and elliptic curves are the simplest example of abelian varieties. So what makes them special? So let's explain the two words, abelian and varieties, because they have become important in cryptography too. Variety means that it's defined by algebraic equations. So in this case, the algebraic equation is just a single one. It's y squared equals x cubed plus ax plus b. And abelian means that they have an abelian group law. And in the case of elliptic curve, this group law is very simple. By using the Bezout theorem, you can prove that any line intersects the elliptic curve in exactly 3 points, counted with multiplicities. And here I'm cheating a bit because you need to be in an algebraically closed field for this to be true. Otherwise, it could be intersected in less than 3 points. But let's think algebraic closure, because that's what we always do. So let's think complex numbers, for example. Then every line intersects in exactly 3 points if you count with the appropriate multiplicity. And then you just want to define a group law such that any 3 points that are on the same line sum to 0. And then you prove that this group law is well defined. It has a neutral element, which in this drawing is not shown in the picture, is what we call the point at infinity. It's some projective point that lies out of the affine plane. So you can imagine it as being all the way up to the top. Like if you follow the y-axis and you go to the top, there lies the point at infinity. It also lies all the way to the bottom. It's somehow the geometry is a bit twisted for these objects. But yeah, other than that special point, which needs to be treated, which needs lots of work to explain, it's just an algebraic equation. And this group law turns out to be commutative. It's not very difficult to see. So if, for example, like in this picture, P, Q, and R are 3 points that sum to 0, and then because of the way the group law is defined, the opposite point to R becomes the point symmetric to the x-axis becomes the opposite of R. So the point minus R is equal to P plus Q. So it's this point here on the bottom. And it's easy now to see that the group law must be abelian, because if you swap the rows on P and Q, you get the same result. So this is something that cryptography has been using for decades now, because you can use the group structure of the elliptic curves to define a cyclic group in some cases over a finite field, and then you use this cyclic group to define to do Diffie-Hellman key exchange and other kind of properties. But isogeny-based cryptography is not really interested in a single curve on its own. We just don't look at one curve, y squared equals x cubed plus x plus ax plus b. Isogenies are maps between elliptic curves. So in a way, they are the natural concept of algebraic morphism, of morphism between abelian varieties. And so when we work with isogenies, we always consider the set of all elliptic curves with isogenies between them, with all the possible maps between them. And so the sets we can constrain them in different ways and obtain different classes of elliptic curve with isogeny relationships. So formally, an isogeny is an algebraic map between elliptic curves. Algebraic meaning that it is defined by polynomial, by rational fractions. And it has one extra condition, and you can choose any one of the 3 conditions listed here. You can even say that it is a surjective group morphism. So if you see how the isogeny maps the points, it must respect the group law. It must respect the group structure. So in particular, 3 collinear points must be sent to 3 collinear points. So the isogeny must respect straight lines, must preserve straight lines in a sense, and must do so surjectively. So this is only possible for, again, algebraically closed fields. And then usually in practice, when we implement cryptographic scheme, we don't work with algebraically closed field. We work with finite fields. And then just think of what the theory reduces to if you take away all those algebraic points in the algebraic closure. Equivalent to this property, it is just the fact of being a group morphism with finite kernel. So these two are equivalent. You can, if you have finite kernel, you are surjective. If you are surjective, you have finite kernel. And something that's even more striking, you don't even need to impose the group structure. You just need to say that the isogeny is a non-constant map. You cannot send all the points to a single point, but just non-constant suffices, and it must be, it must preserve the point at infinity. So in terms of groups, it must preserve the identity element of the group. And this is sufficient to prove that the isogeny is a group morphism. And so in particular, it has finite kernel and is surjective. So in any of these conditions is equivalent, and in any of these conditions, we call this map, this algebraic map, an isogeny. And I will say isogenous, the 2 curves are isogenous if an isogeny, there exists an isogeny between them. So that now we have a class. And the reason why I'm really using this word as a class is that we can show that having the relationship of having an isogeny is something that is, first of all, it's reflexive. Any curve has isogenies to itself. The most simple isogeny you can think of, it's of course the identity. So the isogeny that sends a point to itself, that's an isogeny, pretty trivial one. A less trivial one, for example, is the multiplication by n map. On any curve, call it E, you can define an isogeny, and actually this is even something stronger, it's a homomorphism, that maps a point to n times the point. So we need to check that this is an isogeny, so we need to check that it satisfies the conditions of the theorem above. It is certainly algebraic because the additional law is given by algebraic formulas. And so if you compose these algebraic formulas m times, what you get is an algebraic map, polynomials that define your multiplication by n. and it sends the point at infinity to the point at infinity, because of course m times 0 is also 0. So we're done, it's an isogeny. And then obviously you can also check that it is a good morphism with finite kernel. This is something you need to prove, but if you know a bit about elliptic curve, you will know that the set of points of order m is finite. And it turns out to be surjective if you're working over the algebraically closed field. So this is one first example, which shows that being isogenous is a reflexive relation. Then you need to show that the relation is transitive, so that if you have an isogeny from a curve to a second curve, from let's say an isogeny from A to B, and then an isogeny from B to C, then you also have an isogeny from A to C. And this is just the composition of isogenies, because of course these are good morphisms, so you can compose them as algebraic maps. They will still give rise to algebraic maps. So a composition of isogenies is still as an isogenous. So being isogenous is a transitive relation. And the last non-trivial bit is to show that it's symmetric. Whenever you have an isogeny from some curve A to some curve B, then you have an isogeny that goes from B to A. And you may have more than one isogeny, but there is one in particular that is called the dual isogeny, and that's always used in all computations with isogenies. So let's give a concrete example, so just to touch these objects. Here I have two elliptic curves defined over the finite field with 11 elements. And of course, because now we're a finite field, you don't have this nice shape, turtle shape that I showed before. You just have a finite number of dots, which represents the point of the elliptic curve. And again, I haven't represented the point at infinity because that is difficult to show in this kind of drawing. You will need to represent the projective space to be able to represent that point. So imagine that there is one extra point. Both curves, the one on the left and the one on the right, have one extra point at infinity that is not that you are not seeing right now. And then this map, defined by these equations, by these polynomials that I have there in the lower left corner, x squared plus 1 divided by x and y times x squared minus 1 divided by x squared, we can show, it's easy to check that this map is an isogeny. It certainly is algebraic because it's defined by algebraic maps. And then you need to check that the point at infinity is sent to the point at infinity. Well, this is not entirely obvious because these maps are singular at infinity, so they just don't give any results. So we formally just say that the point at infinity is the point at infinity, is sent to the point at infinity. But it's not too difficult to check that this is a map with finite kernel, and the finite kernel is just defined by those points that make the denominators go to 0. So the only kernel point is the point that is pictured in red now on the left. The only kernel point other than the point at infinity, of course, is the point that is pictured in red on the left, and that's the point of x coordinate equal to 0. Sorry, I thought I had disabled this. So it's the point that has x coordinate equal to 0. And this point is thus mapped to the point at infinity on the right. Some other things to remark on this example. This is a degree 2 map. It's a degree 2 map in the sense that it is a 2-to-1 map. If you look on the right, each point has either 2 preimages or 0. But the fact of having 0 preimages is just an artifact of being working over a finite field. As I said, an isogeny must be surjective. So if now we go to the algebraic closure, we will see every point eventually getting exactly 2 preimages. And so the fact that this map has degree 2 is reflected, well, first of all, in the polynomials. As you can see, it's essentially defined by degree 2 polynomials or degree 2 rational fractions. It's reflected in the fact that it is a 2-to-1 map. And this degree is a very important number that you attach to an isogeny. You can think of it as a measure of the complexity of the object. Really, in terms of, I guess, information theory, the larger the degree, the more isogeny of that degree you will get from a single elliptic curve. And so, yeah, essentially, the degree is a measure of how much data you need to represent the isogeny. This is really what the degree is. So we will usually work with small degree isogenies, large degree isogenies. We will play around with them, trying to go from large degree to small degree, and then other tricks will be using composite degree isogenies. So I will repeat the name, the word degree a lot. So keep this in mind. Anytime you have an isogeny, you have this degree, which I haven't defined, but you can get a feeling of what it is. It is essentially a measure of how much information you need to define the isogeny. And then just one last observation, like this is in a sense a generalization of an algebraic map over the multiplicative group of a finite field. And so if you think of degree to isogenies, really the analog of a degree to isogeny would be the squaring map. The squaring map over a finite field, it's a 2-to-1 map because, of course, x and minus x have the same square. It is surjective if you go to the algebraic closure, meaning that over the algebraic closure, any element gets a square root. It has finite kernel. The only elements in the kernel are 1 and minus 1. So it really behaves like an isogeny. It's a very trivial example of an isogeny. But it's something that it's used a lot. A lot of algorithms, famous algorithms on elliptic curves, essentially come from generalizing algorithms for finite fields, for the multiplicative subgroup of finite fields. So for example, think factoring, the elliptic curve factorization method, comes from the p-1, p+1 factorization method. And in the same way, you can use isogenies to generalize some algorithms that work with the multiplicative group structure of finite fields. And then one last slide of introduction to isogenies in a sense. As I said, when we, sorry. I guess you are seeing this notification popping up. I'm just trying to.
Not disturbing. Yeah, you can.
Yeah. Some of those may even be confidential. I'll just try to. I'll just close my browser so that I will get less notifications. And I don't know. Yeah, something broke in my. Oh God, it's a lucky day today. I guess dbus or some other bugs in Linux.
Yeah.
So. Yeah, the thing I said before is that when you work in isogeny discretography, you do not just look at one elliptic curve. You do not just look at two elliptic curves and as an isogeny between them. You really look at a class of elliptic curves, an isogeny class of elliptic curves, curves such that there are isogenies between them, and the isogenies that connect them. And then you make several restrictions depending exactly on what kind of properties you want. And so obviously when you do this, the natural thing to do is to define an isogeny graph, which is a graph where the vertices are elliptic curves. So here the black dots in this picture represent elliptic curves, and the edges represent isogenies according to some restrictions. So the usual restriction is that, first of all, instead of looking at elliptic curves in general, like as I show them, we look at elliptic curves up to isomorphism. So that would mean as elliptic curves up to isogenies of degree 1, in a sense. Because yeah, isomorphism is something very simple. We want to ignore it. So let's forget about this. Let's just think of a class of isomorphic elliptic curves as a single element in my graph. And what's very convenient is that we even have a number that lets us classify these isomorphism classes. You may have heard of the J invariant. The J invariant is an algebraic number attached to any elliptic curve, such that two elliptic curves have the same J invariant if and only if they are isomorphic over the algebraic curve. So this is very convenient because that means that whenever you want to represent an isomorphism class, you just need to say one number and that's it. Things get more complicated when you go to higher dimensional abelian varieties, but in the case of isogeny of elliptic curves, it's very convenient. So we usually use either J invariant or other invariants, similar related invariants. Doesn't really matter. But the important thing is that you can think now an elliptic curve is not anymore some strange curve, it's just a number. That's what an elliptic curve is. And then the isogenies, well, something that we usually like to do is, for example, restrict to the isogeny class of supersingular curves. I will say later what a supersingular curve is. But so yeah, we take all supersingular curves over a finite field, and then we take the isogenies of a fixed degree between them. So for example, what you're seeing in the picture on the right is the graph of all supersingular elliptic curves over the finite the algebraic closure of the finite field with 97 elements, and the isogenies of degree 3 between them. And now, first of all, it turns out that this isogeny class is finite. Even if the algebraic closure of P is infinite, there is only a finite number of isomorphism classes of supersingular curves. So we can really write down completely the isogeny graph as long as we keep them small, which of course we won't when we do picture lithography, but in these small examples, you can just enumerate all the supersingular elliptic curves. And these graphs have the nice property of being L+1 regular. Now, you need to be a little bit careful. You need to count multiplicities of the edges in the proper way. But let's say this is just a technical detail. It essentially is a technical detail. So when you do things properly, these graphs are L+1 regular, meaning that from every vertex, there are exactly L+1 edges going out. So if you look at this graph, every vertex here has exactly 4 edges, and you see in the middle there is this double edge between these 2 points. That's exactly what I mean when counting them properly. You should distinguish isogenies if they are not behaving the same, and sometimes you need to count isogenies more than once. But like these technical details are very simple to handle, and so you just ask an expert and he will tell you how to do it. It's easy. And now what we like about these isogeny graphs and what have made them so useful in cryptography is that they have very nice properties that make them similar to random graphs. What I'm referring to is the fact that these graphs are expander graphs. And even better, they are the best possible expander graphs. They have the Ramanujan property. I'm not going to define properly the Ramanujan property because this is a technical definition that needs to look at the adjacency matrix on the graph and then say something on the eigenvalues, and it doesn't really give you an intuition of what this is doing. But really, the intuition of what an expander graph is, it's a graph that has, essentially, it has a short diameter. You can get from any point to any point with a small number of steps, logarithmic in the number of vertices. So because of this means that each pair of vertices is never too far from one another. And in particular, what we use a lot in cryptography is the fact that if you start from one vertex and you start walking randomly, with very few steps, you could be anywhere in the graph. And said more properly, like a random process on this graph reaches the stable distribution, which is essentially the uniform distribution, very quickly in just a logarithmic number of steps. Which is very good for cryptography because, yeah, you understand essentially what you want to do is you want to create confusion. You want, with a small number of operations, land somewhere in the graph which is indistinguishable from other zones, other places in the graph. So there is a very rich theory behind this, which is extremely fascinating. There's many different ways to look at these graphs. You can look at them as isogeny graphs. You can look at them as Heck operators, like their adjacency matrix. You can look at them as a Heck operator acting on modular forms. There is a theory of Brand matrices that's associated to that. We will soon see another way of understanding these graphs, which is through quaternion algebras and maximal orders. So the mathematics of this are extremely rich and sometimes a bit scary, I must admit, because yeah, it picks ideas from various sub-branches of number theory and even related topics. So it's quite hard to get a full vision of what's around all this space. But it's definitely fascinating, and the results you get are very powerful. And there are many different ways to prove interesting theorems for cryptography. So yeah, I guess this was the introduction to isogeny-based crypto in a sense. I didn't define much. I just gave you a sense of what's involved. And now let's maybe just relax a bit. So first of all, if you have questions on the technical side, ask them now. I'll make a few seconds of silence. Okay, it seems there are no questions. They can come later.
Yes. Diameter. So you mentioned about diameter. Is it better to have small diameter or large diameter in terms of cryptography?
Well, it depends what you want to do, of course. an extremely large diameter graph is not very interesting, because like if your diameter is n, this, like, let's say you have n vertices and your diameter is n, I think the only possible graph then it's a line. What do you do with a line in cryptography? It doesn't look very useful. So of course, to the extreme, it's not very interesting. For what we want to do in cryptography, in isogeny-based cryptography, we are very happy to have this Ramanujan property, which is really the optimum, because it means that essentially you can approach the uniform distribution with the minimal number of steps. When I say minimal, it means like, yeah, in an asymptotic regime, like where you have families of expander graph, like let's say you increase a P. This is the asymptotic regime. P, the characteristic of the finite field, is what parameterizes these graphs. For each P, you have a different supersingular isogeny graph. And when you make P go to infinity, the Ramanujan property is the best you can hope for. It reaches the optimum bound. And so we can prove that the diameter is as small as possible for these graphs in an asymptotic sense. And we can even very precisely give formulas for how many steps you need to take in a random walk in this graph to approach the uniform distribution up to a certain distance. So you can really give precise statements on the, for example, cryptographic statements like indistinguishability of distributions, like between the process that picks a curve, a supersingular curve uniformly at random, and the process that starts from some vertex and walks randomly, what's the distance between these two distributions? You can give an exact quantification using the Ramanujan property, and then using this, you can deduce security parameters for your systems. So in this sense, yeah, the smaller the diameter, the better the parameter will be for the system. But then sometimes you can live with less. I mean, if you are not Ramanujan and you are just a constant factor off from the optimum, you can still do lots of things. And in the end, a lot of our schemes in isogeny-based cryptography do not exploit the Ramanujan property to the maximum, just because for technical reasons sometimes. Like if you can think, for example, SIDH, for example, was very far from using walks as long as the diameter. The length of the secret walks in SIDH was half the diameter, roughly. And in the end, this is one of the reasons why SIDH got broken. Not the only one, but it certainly had an impact. So sometimes we just cannot, SIDH could not work that long for technical reasons, and sometimes we have to live with that. But it's certainly good to have short diameter in general, if what you want to do is have statements on indistinguishability of distributions. Okay, let's relax a bit and let's talk about the history of isogeny-based crypto. So why do we use isogenies in cryptography at all? Where do these things come from? Well, of course, they come from elliptic curves. So they were never unknown to cryptographers. And actually, the first reason to look at the isogenies was for point counting. So definitely not for defining new schemes, but just for using elliptic curve cryptography. Because if you remember in the beginning of elliptic curve cryptography, one difficult question was, okay, elliptic curves look great for doing cryptography, but I need to find an elliptic curve which has a group of prime order or near prime order. How do I go with that? Because even counting the point of an elliptic curve is something non-trivial. And then there is Hopf's algorithm that comes and shows that you can do that in polynomial time. But then still, that was quite slow. And then there are the optimization given by Elkis and Apkin, which led to the famous SEA algorithm. And they were the first to introduce isogenies to cryptographers, I would say. It's through these works that cryptographers were made aware of isogenies. And then, yeah, cryptographers started thinking of isogenies, group morphisms. So if an isogeny is a morphism from one elliptic curve group to another elliptic curve group, that means that it transports the group structure. So it also transports the discrete logarithm problem. And so I can use isogenies for security reductions, because I can show maybe that the discrete log is as hard on this curve as it is on this other curve. And so this is essentially how isogeny-based cryptography was born, was by rather thinking about security proofs, like how can I find an isogeny between two elliptic curves which are isogenies? One thing is for the curves to be isogenious. One thing is to really find the isogeny. And so is this computable? Is this easy or hard to compute? Are these security reductions effective or not? And this is how people started thinking of isogeny graphs and start thinking about really the algorithmic aspects of isogeny graphs. And this concretized in the 2000s, second half of 2000s, where people really started defining like cryptography schemes, which were not based on the discrete logarithm problem, but really on the property of isogeny graph. So the very two first examples, which were nearly simultaneous, were the hash functions Charles-Goren and Lauder, which is a very basic building block, which is used essentially everywhere in isogeny-based in supersingular isogeny-based cryptography. It's behind the scenes in all these schemes, and it is behind the scenes in SQIsign. And the other one was the Couvagne and Rostov-Stestolbunov idea. So these were two independent discoveries of the same key exchange mechanism, which is the ancestor of SQIsign, if you're maybe familiar with the more recent key exchange schemes based on group actions of quadratic imaginary class groups. SQIsign does it on supersingular curves, but the ancestor, the Couvagne-Rostov-Stestolbunov key exchange, did it on ordinary curves. So these were the very first two ideas, which essentially founded isogeny-based cryptography, although it took a while before people really started believing that isogeny-based cryptography was more than just a number theorist crazy idea, just something completely theoretical. And that turning point came with the discovery of SIDH, the supersingular isogeny Feldman, which essentially combines a little bit the two ideas of Charles-Goren and Lauder and Couvagne-Rostov-Stestolbunov. Because it is a key exchange, it tries to mimic a little bit the Couvagne-Rostov-Stestolbunov key exchange, but it does so on the supersingular isogeny graph, using some advanced tricks to make the diagram commute and to get to the same shared key in the end. And this was the very first efficient key exchange based on isogenies. And this is why people started getting interested. And now probably you know the story. If you've been around crypto and post-quantum crypto, you know the story. 2017, a NIST calls for submissions. SIDH is submitted to the NIST submission under the name of Psych. It is remarkable for being the most compact public keys and ciphertext in the competition. Everyone is excited about it. Excited to the point that people start researching a lot in isogeny-based cryptography. Comes SQIsign, the commutative SIDH scheme, which has not much to do with SIDH, to be honest, is more related to Couvagne-Rostov-Stestolbunov. And then there are ideas about verifiable delay function, something that's quite orthogonal, not post-quantum, but still using isogenies. SQIsign, our topic of today, and this is just a short selection of topics, but really, in the past 5-6 years, the literature on isogeny-based cryptography has just exploded. There's been tons of publications on the topic. And these has all converged to the point where last summer, nearly exactly 1 year ago, Psych was advanced to the 4th round of this competition. So Psych was selected as an alternate candidate. Somehow the coronation of isogeny-based cryptography as a credible field and something that was maybe not ready to be selected as a standard, unlike lattice-based schemes, but that people were confident could eventually become a standard. And yeah, all this nice story and illusion just collapsed 1 month later when Psych was broken in a spectacular fashion using the theory of abelian surfaces. So something more general than elliptic curves. Elliptic curves are the abelian varieties of dimension 1, while abelian surfaces are the abelian varieties of dimension 2. And yeah, the word a little bit collapsed on the isogeny-based crypto world community as we scramble to understand the extent of the attack and the consequences and what was broken and what was not broken. And now 1 year removed from that attack, we can confidently say that SIDH, Psych are dead. Makes us all very sad. It certainly doesn't make a good press for isogeny-based cryptography, because now people have a hard time believing us when we say that the scheme is secure. Derivatives based on SIDH are obviously also dead. So Sheta, one of the schemes that was derived from SIDH, for example, also is not usable. But a lot of isogeny-based cryptography still holds. And in a sense, we must thank SIDH for having spurred so much research that has led us to diversify so much the field that we have now many different schemes, which are all based on isogenies of elliptic curves and which are not vulnerable to these attacks based on higher dimensional Bingham varieties, and which, as far as we know today, seem to still hold the ground. Like the attacks on site really do not seem to affect at all these other schemes. And so this includes also SIDH related schemes that, unlike SIDH, do not transmit points of the curves. So for example, SIDH based signatures, they are still secure as far as we know. There is no reduction in the security of these schemes. They are not the most popular because they are not very efficient, but they are definitely usable. SQIsign and this Kubeni-Rostov-Stoguna scheme are also completely untouched by the attacks. Verifiability functions, SQIsign, of course, the topic of today, these are all still safe. And in the end, what is still safe is the supersingular endomorphism ring problem, which is the fundamental problem. Like it's the discrete logarithm of supersingular isogenies, if you want. It's the problem that if you can break that, then you break everything, except ordinary isogenies, but then we won't be left with much. So this problem is still unsolved, still holds the ground. So yeah, maybe SIDH was just a misstep, and the rest of isogeny-based cryptography will keep living happily ever after. But this is something that only time will tell. So if you want to know more and see more about all the different varieties of schemes and assumptions, I invite you to look at this website, isignbrokeny.github.io, which is a bit incomplete. I should complete it. I promise I will by the end of the summer, which tries to map out the space of all possible problems and what's broken, what's not broken. And now finally, I come to the topic of my talk today, which is this famous overview of SQIsign, where now I have to go back a little bit to the mathematics and give you a little bit more definitions. I must define some objects more to come to SQIsign. I will do this quickly. I won't enter into the details because, of course, it's quite deep. But I just want to give you a sense of what's behind SQIsign, and I want to convince you that it is not so difficult. The algorithms are technical, there is no doubt about that, but the general intuition is quite simple. And with time, we hopefully will make all the algorithms even simpler so that everyone can manipulate these objects without even thinking. Any questions so far? Okay, so let's talk about something that has nothing to do with SQIsign. Just a very loose analogy of how SQIsign works. So signing based on factoring. Let's take an integer n, which is the product of two primes, p and q. Of course, this is the basis for RSA, as you know, but it's also the basis for the Rabin signature, which is something that is probably reduces to factoring over factoring integers. What's the trick in Rabin signature? Rabin signature is based on the fact that knowing the factorization of n is essentially knowledge of a chapter, something that allows you to do things that someone who just knows n but not its factorization is not able to do. So when you look at Z mod n, the ring of integers modulo n, some operations are easy to do. You can easily multiply integers, you can easily invert integers, that's just the extended GCD algorithm. But some algorithms are hard. It's hard to compute square roots. In fact, it is probably equivalent to factoring n. If you can find arbitrary square roots modulo n, then you can factor n. And more generally, taking nth roots for larger n is also hard, and this is the basis of RSA, of course. But if instead you know the factorization of n, then you know the Chinese remainder decomposition of the ring Z mod n. You know that it is isomorphic to Z times P, Z mod P times Z mod Q. And in this world, when you have knowledge of the structure, everything becomes easy. You can compute square roots, you can compute nth roots, you can do everything. So in a sense, like you have the same object, it's still the ring of integers modulo n, but you have two different ways of seeing it. One is the hard way, the way that it's accessible only to the public, the only way that it is accessible to the public, so n without its factorization. And there you are limited in what you can do. And then you have another word, the word of I know the factorization, where everything becomes easy. And so this is the word of the owner of the secret key. And then Rabin's scenario is just a joke. It's super simple. It's just if I want to send a message, M, I compute the hash of this message, I add some randomness, and then I compute the hash, and then I take a square root modulo N. I can do this because I know the factorization, so I know the secret. Okay, you need to try more than once because maybe I get a number which does not have a square root modulo N. But so then if I do, I just change the randomness and try again. And then the signature is just the square root and the randomness that I used with the message. And to verify what you do, well, it's very simple. You square the value S, you square the square root, which is something that everyone can do because multiplication in Z mod N is easy. And you get the hash, and you compare it with the hash of the message with randomness, and you just check that they are the same value. And this is verification. So this is super simple. It's a very simple signature. And in a sense, SQIsign is as simple as this. So there is one first difference is that SQIsign is not a hash and sign method. It's a Sigma protocol. It's an identification protocol that then is made non-interactive using Fiat-Shamir transformation. So in a sense, these are technicalities, although they are not little technicalities. So if you are a cryptographer, you know these words, you know about this stuff, and it's all familiar to you. If you're not a cryptographer, this is totally out of your knowledge, I guess. And then, yeah, maybe just stick to this simple picture. Let's think, yeah, it's something like this. It's something where the owner of the secret key has some operations that are easy for him, that he can easily do, whereas the verifier doesn't know the secret key, and so he's limited in the kind of operations they can do. And so now I need to introduce these objects because, of course, the word of isogenies is not as simple as the word of Z mod N and Z mod P, unfortunately. So I'm going to build towards something that is called the Darwin correspondence, and I will try to be relatively quick on this. So now I can say what a supersingularity curve is. A supersingularity curve is a curve that satisfies the properties that are listed here. So first of all, you can prove that every supersingular curve is isomorphic to a supersingular to one defined over FP squared. So in particular, its J invariant is defined over FP squared. So even though we consider the set of all supersingular curves over the algebraic closure, in the end, we can just focus on a finite set. And in the end, we can do all computations in a finite field of P square elements. Every isogeny is also defined, every isogeny of supersingular curves is also defined over FP squared. So again, also the isogeny computation all happen over FP squared. Every endomorphism is also defined over FP squared. And this is very important because we need to compute lots of endomorphisms, it's design. And every endomorphism satisfies a quadratic equation. Now, what do I mean by this? Endomorphisms, so endomorphisms are just isogenies from a curve to itself. And if an isogenous goes to a curve to itself, you can do two things with it. You can compose it. So for example, when I write omega square, I mean take an endomorphism and apply it twice. So multiplication is composition of endomorphisms. And you can add two endomorphisms together. What does it mean to do omega plus alpha, for example? Well, it means I take a point, I evaluate omega on it, then I evaluate alpha on it, then I take the result and I add them together. So this is omega plus alpha. So clearly the endomorphisms behave like a ring where you have a well-defined multiplication and a well-defined addition. And now you're interested in what's the ring structure of these endomorphisms. Well, the first thing you notice is that every endomorphism satisfies a quadratic equation. This is a powerful theorem, tells you that essentially every endomorphism has a minimal polynomial, which is omega squared minus T omega plus n, where T and n are two integers. So quite powerful theorem. And already once you know that there's not many possibilities for the abstract structure of this ring. And indeed, you can prove that a supersingular curve is an elliptic curve such that its endomorphism ring is isomorphic to a maximal order in a quaternion algebra ramified at P and infinity. Now, of course, this is a mouthful. It's quite complicated. And now I'm going to just explain what this object is. But this is the definition of a supersingular curve. A supersingular curve is a curve that satisfies this property of having an endomorphism ring isomorphic to a maximal order in quaternion algebra. So before giving the definitions, let's start with an example. It's always easier. So let's take a very special curve. Let's take the curve with J invariant 1728, which has equation y squared equals x cubed plus x. This curve is supersingular over the finite field with p elements if and only if p is congruent to 3 mod 4, to minus 1 mod 4. And if this curve is supersingular, then it's an endomorphism ring. It's essentially generated by 2 elements. There is a typo, but I hope most people will notice. The generators are not exactly those. There is a division by 2 that I forgot to put there. I will fix it later. But so yeah, modulo small typos. There's 2 important endomorphisms which essentially generate the endomorphism ring. One is the Frobenius endomorphism. What is Frobenius endomorphism is just taking the coordinates of your points and raising them to the p power. So this is something that acts like the identity over Fp, but acts non-trivially over the algebraic closure. And then you can show that the endomorphism, the Frobenius endomorphism, when you apply it twice, acts exactly like multiplication by minus p. So in a sense, the endomorphism, the Frobenius is a square root of minus p. And then you have another map, which it's even more than endomorphism. It is an automorphism. So it maps points 1 to 1. It's the map that we usually denote by iota. And this is the map that maps a point with coordinate x, y to the points minus x, I times y, where I is a square root of minus 1. And now it's easy to see, like if you apply iota twice, what you get is xy gets sent to x minus y. And so this is the negation map, the map minus 1. So iota is a square root of minus 1. And by working things explicitly, it's very easy to check that iota and pi do not commute, they anti-commute. So if you apply first pi and then iota, is the same thing as apply first iota, then pi, and then negating the output. So yeah, this shows that the endomorphism ring is certainly a bit complicated because it's a non-commutative ring. You have something strange going on. And exactly will be the quaternion algebra. So it will be a ring inside the quaternion algebra generated by pi and iota. So what's a quaternion algebra? From now on, I'm going to assume that p is congruent to 3 mod 4, exactly like in the example before, just because it makes notation easier, simpler. This is not strictly necessary, but it's very convenient, and we do it all the time, and it's done in SQIsign. So the quaternion algebra ramified at p and infinity, it's a 4-dimensional vector space over the rational numbers. So it's essentially something generated by 4 elements. One element is just 1, so it's just one component is just the integers, the rationals. And then there is 3 elements, I, j, and k, we usually denote them like that, which satisfies a list of multiplicative relations. The relations are I square equals minus 1. So if you remember, this coincides with the iota of my elliptic curve. J squared equals minus p. So this coincides with the Frobenius of my elliptic curve. And then the anti-commutation I times j equals minus ji. And this is what we call k, usually. So this is a well-defined, non-commutative division algebra, meaning that every element has an inverse, but it's not a field because it is not commutative. And so interesting properties are that all elements are quadratic algebraic numbers, so all elements satisfy a quadratic equation. And if you localize the different primes, you get different structure. For example, essentially, if you complete at any prime L other than the characteristic P, other than P, then what you get is essentially 2 by 2 matrices. So this is something that everyone, I guess, is familiar with. You all understand what 2 by 2 matrices are. Maybe you understand a little bit less what the L-adic numbers are. But essentially, we're talking about 2 by 2 matrices. If we look locally at each prime, and there's only 2 places where things are. I see a raised hand. So yeah, please ask the question.
No, sorry, someone has just joined. Maybe he has joined.
Okay. I thought that was a question. Too bad. Okay, so yeah, and then yeah, there's the other 2 places where things behave a little bit different, and this is why the algebra is ramified at p and infinity. if you localize at the infinite place, you get Hamilton's quaternions, and if you localize at P, then what you get is a division algebra. This is essentially the properties. But yeah, these are not so important. Won't help you much understand SQIsign at this level of detail. Although they're very important because they really gives, especially the localization itself, the fact that essentially you can represent elements of the quaternion algebra as 2x2 matrices. That's something that we use a lot in computations in practice. And then if you thought that you could work on isogeny-based cryptography just to escape lattices because you don't like lattices, well, I have very bad news for you, because again, we have lattices. They're popping again. There is a very natural definition of norm for a quaternion algebra, which is just the, so first of all, there is a notion of conjugation, because you see, like in the complex numbers, you have I and minus I, which are conjugate to each other. And so you can define the conjugate of any complex number as just flipping the sign in front of I. Well, the same here, we can define the conjugate of some number A plus B times I plus C times J plus D times IJ as just flipping the signs in front of B, C, and D. And then we can define the norm, the reduced norm of an element, as the product of the element and its conjugate. So this becomes essentially the formula. If I have a quaternion with coefficients A, B, C, and D, so this is just a vector of 4 integers, or sorry, of 4 rational numbers, A, B, C, and D, then I define its norm as being A squared plus B squared plus P, this P, which is the ramified place for the quaternion algebra, times C squared plus D squared. So this is an algebraic norm. It is a multiplicative function. If you take its square root, it defines a metric, the square root of the difference of 2 quaternions. And essentially you have a 4-dimensional vector space with Q vector space. You have a notion of metric, so essentially you can define lattices, because now you can define the modules inside of this vector space. And you also have a concept of an integer, exactly as you do for Q, for the rational numbers. We say that an element whose norm is integer, we call it an algebraic. And so this will play a very special role in SQIsign. And so you see now we make lattices appear again, but these are very simple lattices. Unlike the lattices you use in lattice-based cryptography, these are very small dimensional lattices, because my quaternion algebra is a dimension 4 vector space. So of course my lattices are going to be 4-dimensional lattices. With the rank of the lattices, usually we say, we don't say the dimension, the rank of the lattices will be exactly equal to 4. So whenever we have a full rank lattice, so a rank 4 lattice inside the quaternion algebra, we call this a fractional ideal, or just a lattice, you choose, it's the same. And whenever all the elements of a fractional ideal are algebraic integers, then we say that this is an integral ideal, or we just don't say integral, we just say ideal. I will keep saying ideal from now on, and I will mean integral ideal. And so if it's an ideal, and then another special case is the case where these integral ideals are also subrings of the quaternion algebra. In this case, we call them orders. Okay, so this is just some naming conventions. And one important thing is that the same way that you can use the norm to measure the size of some algebraic integers, you can also use the norm to measure the size of an ideal. You define the norm of an ideal, of an integral ideal, as the PGCD, as the GCD of the norms of all the elements of the ideal. This is something that is well defined. It's a finite integer, and it's essentially a measure of how sparse the lattice is. That's essentially what the norm is. And then one very important concept is the concept of a left and a right order associated to an ideal. So whenever I have an ideal, I can associate a subring to it, a subring of the quaternion algebra to it, which is its left order. This is essentially the stabilizer of the ideal. So it's the set of all those quaternions such that when you multiply, so all the quaternions alpha, such that when you multiply alpha by the elements of the ideal, you obtain again an element of the ideal. And now, because the ring is non-commutative, you must be careful whether you multiply on the left or on the right. So if you multiply on the left, this is the left order. And if you multiply on the right, this is the right order of an ideal. So to every ideal, you can associate these two orders which are very important, and which will play out like I'm going to show in a second. So now I have defined all the concepts. I need to define the Dorian correspondence, which is this very beautiful theory that puts in correspondence supersingularity curves with maximal order of quaternion algebras, and then we have all a dictionary of how things correspond to one another in this world. But before, I need to define a concept of equivalence of maximal orders. So we say that two orders are the same, have the same type if they are conjugate of one another by a quaternion. So you see, if the quaternion algebra was commutative, then there would be like the type would just contain one order, because alpha or alpha minus one commutes, cancels with alpha, and then you just get O again. But here, because the ring is not commutative, it's a bit more complicated. But we call the maximal order type the equivalence class of orders up to conjugation. And the theorem by Dorian tells that maximal order types, so these equivalence classes of orders or maximal orders, are in one-to-one correspondence with supersingular curves up to isomorphism and up to Galois conjugation. So the correspondence is a bit twisted because you also need to be careful about Galois conjugation in FP square, but it gives you really a mapping between essentially every pair of supersingularity curves up to isomorphisms corresponds to only one possible order type for which is their endomorphism ring. And so this is the beginning of Dorian correspondence. And Dorian correspondence, I guess the best way to visualize it is like this. Whenever you have an isogeny, so now look at the bottom of the figure, you have an elliptic curve E, an elliptic curve A prime, and an isogeny between them. And then to this corresponds on the quaternion level, a left order O, which is going to be isomorphic to the endomorphism ring of E, a right order O prime, which is going to be isomorphic to the endomorphism ring of E prime, and a connecting ideal, A, which is going to represent the isogeny. So the Dorian correspondence is an equivalence of categories that roughly gives a correspondence between orders, maximal orders, and supersingular curves, and ideals and isogenies. Again, we can define classes of an isogeny. So we say that two ideals are in the same class if they are the same up to right multiplication by a quaternion. So alpha A and B are the same class if A is equal to B times beta for some quaternion beta. And this corresponds to a notion of isogeny class, which is given by this dictionary. So on the left side, the word of supersingular curves. On the right side, the word of orders. And so endomorphism of supersingular curves, now we know, correspond to integers of the quaternion algebra ramified at P and infinity. This is the first thing that we said, essentially, that these two things are the same. The full endomorphism ring of a specific supersingular curve is going to be isomorphic to a maximal order inside the quaternion algebra. And we just said that Dorian tells us that this is the almost one-to-one correspondence. It's more a one-to-two correspondence. Like if you take care of the Galois conjugation, then it becomes all explicit. Isogenies correspond to ideals inside these orders, and the left ideal corresponds to the left order of an ideal corresponds to an endomorphism ring on the left of the isogeny, and the right order corresponds to the endomorphism ring on the right of the isogeny. The degree of an isogeny corresponds to the norm of an ideal. So now this is very powerful because computing the norm of an ideal is something that is very simple. You just look at its lattice, you look at the matrix that defines the lattice, and then you can compute its norm, and this automatically tells you what the degree of the associated isogeny is. And then if instead of looking at a single isogeny or a single ideal, we look at classes, so up to equivalence of ideals, then what we get is an equivalence isogenies. Two isogenies, we say that we call them equivalent if they go between the same elliptic curves. So this is what the drawing is trying to represent. The two dots represent two elliptic curves, and we have two isogenies which are in the same class because they go between the same pair of elliptic curves. So this is what we call a class of isogenies, and this class of isogenies will correspond to a class of ideals. So within the set of all isogenies, it's actually even a group, within the group of all isogenies between two fixed supersingularity curves, we can choose one isogeny which has a certain degree by choosing one ideal which has a certain norm. And this is a very, very powerful concept that we use all of the time in SQIsign. And then finally, going back going the opposite way, so taking the dual isogeny, so taking the isogeny that goes back in the opposite direction, is the same thing as taking the conjugate ideal, which is just the ideal of all the conjugates of the elements in the ideal. So this is essentially on a high level what the Dorian correspondence gives you. And now I forgot to add one slide, I must say. The interesting thing is that we get to a situation which is very similar to my loose analogy in the beginning, where you have one word where some problems are hard and one word where all problems are easy. And this is exactly what happens in the Dorian correspondence. If you look at the word on the left, the word of supersingularity curves, then here some problems are easy. So for example, computing isogenies, like starting from a curve and computing a chain of isogenies, is something that you can easily do. But some problems are hard, and the typically hard problem is, if I just give you a supersingular curve, finding its endomorphism ring, finding any kind of description of its endomorphism ring, it's a hard problem. And other hard problems are if I give you two supersingularity curves and no other information than just the equations of the supersingularity curves, finding an isogeny between them, it's an easy problem. Now, if you translate these problems to their analog on the right-hand side, on the side of the orders, all these problems become super easy. Like, well, first of all, yeah, the problem of computing an endomorphism ring is not anymore there. It's more the problem, I give you a maximal order and now find a curve whose endomorphism ring is isomorphic to this maximal order. So going the opposite way, this is an easy problem. So going from the orders to the supersingular curves is something that we know how to do. But going from the supersingular curves to the orders is something that we do not know how to do. And then if I give you two maximal orders, one that we see as one left order and one right order, finding the ideal that connects them, this is something that we know how to do. This is an easy problem. And if we have one ideal, finding an equivalent ideal, this is also something easy. And the equivalent problem on the isogeny side, this is something difficult. So we are really in the same situation as the Rabin signature, where on the left-hand side, we have a word where some operations are difficult. And so that word is the word where the attacker lives in. The attacker has some hard problems to solve. But the owner of the secret key, and what is going to do to be the secret key? The secret key is going to be exactly the knowledge of the endomorphism rings of our elliptic curves. Well, that knowledge is something that allows us to do all sorts of computation efficiently by just working into the world of orders, of maximal orders of quaternion algebra, doing all the computations there, and then translating those computations to the world of supersingular curves. So this is essentially the intuition behind SQIsign. And I wish I had more time to go more into the details, but I think I already bombarded you with lots of information. So I guess this is a good point to stop with the mathematics and just finish on the the outlook of SQIsign. So what is SQIsign? And here I put a diagram, which is a very simple summary of how SQIsign works. SQIsign is something very basic. I regret not having put an animation here. Can you see my mouse pointer moving?
Yes, yes.
That's great. So I will just take one more minute because we're really running over time. We'll just take one more minute to show you exactly how things are set up. So the way SQIsign is set up is like this. We have an elliptic curve E0, which is a special supersingularity curve on which everyone knows the endomorphism ring. This elliptic curve always exists. Actually, this is where we always start. We always need to start from some supersingular curve of known endomorphism ring. And so, for example, you can take the elliptic curve y squared equals x cubed plus x, the example that I gave a few slides before. And then tau here is a secret isogeny. It's going to be our secret key. So it's a walk, is an isogeny walk from E0 to some EA, and EA is going to be the public key. So here on the left of this diagram, what you see, it's essentially the key material. E0 is just a public parameter, EA is the public key, and tau is the secret key. And already a very good news is that all this is very compact stuff because the public key is just one J invariant that you need to transmit. And very concretely, this is going to take 64 bytes at the levels of security equivalent to NIST 1. And tau, well, there's many possible ways to represent tau. In the SQIsign implementation, a reasonable way takes 700 bytes, so less than a kilobyte, but it really depends. Of course, you can always regenerate the secret key from the seed, the random seed. So if you really need to compress the secret key, you could compress it down to 16 bytes. This is just your choice, of course. But yeah, so of course, the size of the secret key is not a super important parameter. What's more important is, of course, the size of the things you transmit over the wire. So the size of the public key. And now, how does SQIsign work? Well, SQIsign it's a de-interactivized identification scheme. So it's easier to understand this as an identification scheme where there is a prover that sends some information, a verifier that responds with a challenge, and the prover that responds to the challenge. And so the idea is that the prover will do a random, will compute a random isogeny psi that arrives to some elliptic curve E1. So this will correspond to some random walk in the isogeny graph, which will land on some random elliptic curve in the supersingular graph. And here you see why it's important to have short diameter. The shorter the diameter, the shorter I can take the walk. And so in the end, the shorter will be the signature. Because these things, well, psi will not be part of the signature, but other things will be. So psi is what we call the commitment isogeny. So it's just a random isogeny. It's unrelated to the secret. It's just walking to some elliptic curve. And now E1 is the curve that gets sent to the verifier. The verifier will challenge the prover by sending an isogeny phi, which is again a random isogeny, unrelated to psi, unrelated to the secret tau, because these are things that are not even known to the verifier. It's just some random isogeny, it's public randomness. It's not very important as long as it is not known in advance to the prover. Phi can be any random isogeny. And so the challenge for the prover will be to show to the verifier an isogeny that goes from the public key to the curve E2, which is the final curve of the challenge, of the verifier's challenge. And now, if you look at the diagram, there is, of course, one isogeny which the prover knows, and it's the composition of first I go back through tau, which means taking the dual isogeny to tau, then I compose with psi, and when I compose with phi. But of course, the prover cannot give away this kind of information because this information contains tau, which is the secret key. So we must find a way to find an equivalent isogeny within the class of isogenies from E8 to E2, which is somehow independent from the secret key. And this is where the Dorian correspondence magic works, because this is something that if we had no information on the endomorphism rings, then we would not know how to do it. Essentially, the only isogeny we would know between E8 and E2 would be this long path that goes through tau, psi, and phi. But the power of the secret key is that because we know the endomorphism of E0, we can transport this knowledge to the endomorphism rings of E8, E1, and E2. So we know all endomorphism rings involved. And now we can translate this problem, like if we go back here, we can move this problem from the left column to the right column. And on the right, everything is easy. And so in particular, we will be able to compute an equivalent ideal. So first we compute the ideal that is equivalent to the isogeny that goes through tau, psi, phi. Now that you have this ideal, we re-randomize it to compute some other ideal that is also represent an isogeny from E8 to E2, but this time this ideal will be independent from the secret. Well, to be honest, it is only heuristically independent from the secret. This is one of the big open problems in SQIsign, is proving that it is really independent in an information theoretic sense, and this is something that we do not know how to do currently. Also, lots of space for research, of course. And now, once we have this equivalent ideal associated to some new isogeny, we compute this new isogeny sigma that goes from E8 to E2. And now, this isogeny sigma will be the response that the verifier receives. And then the verifier all he has to do is to check that this isogeny sigma really is a valid isogeny from E8 to E2. If this isogeny is given, then the verifier can be ensured that the prover knew at least one endomorphism of the elliptic curves involved, and this is pretty close to knowing all the endomorphisms of all the elliptic curves involved. And this ends essentially the security proof for SQIsign. So when you put all of this together, it's lots and lots and lots of lines of C code, but it's worth it because it gives you something that is the most compact post-quantum signature known today when you measure together, when you measure the sum of public key and signature size. It is 4 times smaller than Falcon, which is the current record breaker in the NIST competition. And we'll now see with the new signatures that are coming if there is something that beats Falcon in that respect. But as far as SQIsign is concerned, here you have the numbers at all security levels, NIST 1, 3, and 5. And as you can see, public keys are essentially 4 times larger than the optimum you can hope. And signatures are slightly larger, but still very, very compact. Even at the NIST 5 level, they are under the half kilobyte. So they're more at the 1/3 of kilobyte. So extremely compact. And of course, the downside is that all these mathematics, not only they are complicated to explain, but they're also complicated to implement. And so what I'm not showing in this slide is how slow these computations are. And I must say they are pretty slow by cryptographic standards. And this is something that we must do more research in the hope to improve them in the future. So I'm sorry I kept you for a bit longer than was planned. This was my presentation, and please ask your questions.
Thank you so much for this very nice presentation. Also, in order to have this some practical implementation, we need to also convince the implementer. So you need to convince it's so it's another problem maybe. Okay.
I am totally with you. I am totally with you. It is scary enough that I don't know who's going to have the courage to implement this. We did, of course, more than once, and it took us lots of courage. So yeah, this is one problem. We must make all this more accessible so that people are less scared of implementing these things.
Yeah, so now for the participants, if you have any questions, it's now your stage. You can ask your questions.
I have a question, actually. In the page 16, could you back to page 16?
Yes.
If you want, you can take your video. I allow you to share your video if you want.
The endomorphism ring of E must be isomorphic to maximal order, right?
Yes, yes. And the typo is that what I'm defining there is not maximal. Absolutely.
Yeah, the right-hand side is not a maximal order.
Yeah, absolutely, absolutely. That's the type we need. Yeah. I should have written here like there's many different choices you can take as for the generators, but one choice is 1 iota pi plus 1 divided by 2 and 1 plus pi times iota divided by 2. That's one example. So yeah, absolutely, that's a typo. My mistake. It's copy pasting the slides, and then yeah, at some point I just had the Q adjoin iota pi, which is the full endomorphism, the full algebra, and that's correct. But then when I replaced Z, I forgot to update. But you're absolutely right. That's not a maximal order. So there is a typo there.
I understand. And in the next page, page 17, property 2, the extending scalar to elliptic numbers.
Yes.
Makes the quaternion algebra ramified at P or L in this case?
So the fact that this
is not a division algebra, right?
Say it again.
Matrix algebra.
Yeah, it becomes a metric algebra if you complete at any prime other than P.
Eventually, it is ramified at P or L.
It is ramified at P.
P. In the paper, you used the notion of Eichler orders.
Yes.
What is the role of Eichler orders in the SQIsign scheme?
Yeah, that's quite technical, and it requires lots of elements that I haven't explained. So an Eichler order, for those who don't know, it's the intersection of two maximal orders. So why are these important? Well, if we look at what they mean on this diagram, so let's say I have an order associated to A0, I have an order associated to EA, which are their endomorphism rings, and then I'm looking at the intersection of these two orders. and this is an order which is not going to be maximal. So it is going to correspond to some classes of endomorphisms, a limited set of endomorphisms, which essentially behave in some way with respect to the isogenies connecting E0 and E8. And the way they behave is that they are essentially transported by this isogeny tau. So this is why they are important, is essentially because these represent the endomorphisms that we can transport to tau. And now the way these Eichler order are used within SQIsign is that, as I said, from when we set up the system, the only thing we know, the only thing the prover knows, so the owner of the secret key knows, is the endomorphism ring of E0. And then what the prover has to do is to transport the knowledge of the endomorphism ring from E0 to E1, from E0 to EA, and then also to E2. Because the prover needs to know the endomorphism rings of all 4 curves involved, and also of all the curves in between, actually. This is what the prover needs to do. And so the way we do this is by a set of algorithms which we call the effective Dorian correspondence, or sometimes we call them the ideal to isogeny and isogeny to ideal translation. And these algorithms essentially work by pushing the information of the endomorphism ring through isogenies. And to make these algorithms efficient, we use the concept of Eichler orders, because they allow us to essentially transport this information more efficiently. So yeah, this is a pretty high level view, but to get really into the details, like we will need to really get technically into how the ideal to isogeny and isogeny to ideal algorithms work, which would take quite a while. So I hope this is enough to satisfy your curiosity. Otherwise, we can discuss more offline, I guess.
All right, thank you.
Welcome.
Any more questions? What about their formal proof of SQIsign? Is it available? I'm quantum formal proofs and normal traditional formal proofs.
So yeah, the formal proof of security, because it's a Sigma protocol, there are 2 main security properties involved. One is soundness, one is zero knowledge. And so soundness is essentially what ensures to the verifier that the prover knows the secret. And so this is a quite simple proof that essentially shows that if you see 2 signatures, 2 distinct signatures where the curve E1 doesn't change, then you will end up knowing a cycle that passes through the public key EA, and this cycle corresponds to an endomorphism. So you will know an endomorphism of the curve EA, which is not yet as much as knowing the full endomorphism ring, but it's one step towards it. And this is conjectured to already be a hard problem. And then, yeah, essentially then all the security analysis for the soundness amounts to seeing how much information is needed to go from a single endomorphism to the full endomorphism ring. And there is lots of research and several papers on this. So science is advancing on that. But then there is the second property, which is the zero knowledge, which instead is something that guarantees to the prover that when he reveals the signature, he's not revealing any information on the secret key. And now this is unfortunately very complicated in SQIsign, and actually we just rely on a computational assumption, which is essentially tautological, and that says that an oracle which outputs signatures cannot be used in a computational way to gain information on the secret key. So essentially, the zero knowledge property of SQIsign is conjectural, which is, I guess, the same situation as you have for unbalanced Euler-Wiener and other multivariate signature schemes, where you assume that the signing oracle doesn't give information on the secret. And all of this is in the classical random oracle model. So far, there has not been anything done in the quantum random oracle model, because the first block would be to get rid of these computational assumptions on the zero knowledge. As long as we have those, it's very difficult to do anything in the quantum random model.
So what about the using SQIsign in VRF? So you mentioned that isogenies are used in VRF, but they are not post-quantum secure. Can we use SQIsign in VRF?
So I mentioned VDF, verifiable delay functions, which is something different. Although, of course, the verifiable delay function based on isogenies, it's very similar to the VRF based on elliptic curves. It's very much related. So the only thing that isogenies are adding is the delay property. And this is also why the verifiable delay function based on isogenies is not post-quantum, because it's based on discrete logarithms. VRF from isogenies, it's a very difficult topic. As with any other kind of primitives, we don't have very efficient VRFs based on isogenies. It's a very good question. I don't know how to make a VRF out of SQIsign. It's really not obvious because, yeah, this is a Sigma protocol and there is no obvious path from Sigma protocols to VRFs. We need something a bit stronger to get VRFs. So as far as I know, so far no one has proposed a VRF based on SQIsign. And yeah, this would be a very interesting challenge. But personally, I have no idea how to do it.